Hello guys, this is Jin from Donggung University, majoring in semiconductor engineering. In this project, we implemented a 16,000-bit DDR SDRAM. DRAM is a memory that uses the CCL principle through the cell capacitor and the parasitic capacitor of the bit line. Unlike SRAM, DRAM does not store data stably in a latch structure, so the data can change even with a slight timing error. Therefore, timing is very important in DRAM. This is the write operation. We turn on the word line and apply the write signal. We must turn off the word line while the write signal is still present to input the desired value. This is the read operation. Because DRAM reads using CCL, a weak low and weak high occur. We must detect this and convert it into low and high signals. Also, once data is read, the weak low or weak high remains in the cell, so a refresh is required. We use a DSA, which is digital sense amplifier, that can perform all of those roles. In the read operation, we pre-charge to VDD over 2, turn on the word line, then turn on SAN and SAP, and then turn on CG, which is column gate. To store the refresh value again, we turn off the word line, turn off CG, and turn off SAN SAP. For this 16,000-bit design, we used an 8-bank 8-array 25 6-bit cell array structure. Every single cell array is controlled by one column and one row decoder, allowing 64 bits of data to be input and output at the same time. Now let's look at the schematic. This is overall schematic. This is a column and row decoder. For the word line decoder, we try to use bootstrap, but due to parasitic capacitance, stable bootstrap was not achieved, so we used a level shifter. The decoder was designed using the PLD method. This is the Fairfield block. This is the circuit combining NETDFF and PTDFF for DDR operation. And this is the DSA, which is digital sense amplifier. This is the DRAM cell. For the DRAM cell, we could not use the latest process, so we used MIM caps. Therefore, the cell size is large in layout. Here we use a 2T2C structure instead of 1T1 cap to achieve a more efficient read operation using the sense amplifier. This is the pre-charged cell. Now let's look at the simulation. The input D represents the values for the column decoder and R for the input values for the row decoder, which is the word line decoder. We write the same value to all cells in one bank. After that, we can see that all arrays output the exact same written value as in the screen. Now, let's look at the overall layout. You can see that the cells using MIM caps are located one by one. Below them are the Fairfield block and the ETDFF for DDR. Next to them is the decoder that controls all banks and arrays at once. For the decoder signal going to the word line, we use the level shifter in the middle. Now to verify if the layout was made identical to the schematic, let's check LVS and DRC. LVS came out well. As for DRC, since density rules and the path rules were not considered in this project, we can see that it also came out well. Thank you for watching this video.